What's phasor domain? We can represent a time domain signal such as Vm cosine omega t plus theta in phasor domain. You take simply the amplitude and the phase of the signal, and that's your new phasor signal. You can benefit from Euler when you rewrite these signals, and as you can see, the phasor multiplied with aj omega t, which is phasor times the carrier, becomes a new representation of your time domain signal. And the phasor, the capital bold V, is actually now your phasor, which has the information about the amplitude and the phase of the time domain signal. Now we can also rewrite this polar form phasor domain signal as well in rectangular form. If you rewrite this, you can see that the real part of the signal will be Vm. As you can see, the real part of the signal will be Vm times cosine theta, and the imaginary part will be Vm times sin theta. But of course, there's a J at the front because that's the imaginary part. If you want to switch back to the time domain from frequency domain, as you can see, we can take the amplitude, put it at the beginning of the time domain signal. We get the phase, write it next to the omega t signal, and put it at cosine at the beginning, and it is now again back in time domain. So any current signals or voltage signals can be represented in phasor domain. For instance, if you look at the examples, a voltage signal 3.2 cosine omega t plus 30 degrees can be written in phasor or frequency domain as 3.2 with the angle 30 degrees. 30 degrees can be also written as pi over 6, since pi corresponds to 180 degrees. If you look at a current signal, 0.18 sine omega t, we rewrite this in terms of cosine, so it becomes cosine omega t minus pi over 2. Now the amplitude 0.18 and the phase minus pi over 2 are representations for your phasor signal. Now let's look at a new term called impedance. You are all familiar with the resistance, but now we use the complex term for the voltage and the current. Voltage divided by current in terms of complex numbers gives you the impedance. So the real part of the impedance is resistance, which is R, and the imaginary part is called reactance, which is X. So any impedance can be written as R plus JX. So the impedance is not a phasor, but it's a complex number. So it can be written as a rectangular form or phasor form. Now let's look at the case in the case of a resistor. Let's assume the current going through the resistor is IT, which is Im times cosine omega t plus theta. So the voltage will be R times current. So R times Im cosine omega t plus theta. So the magnitude of that voltage will be Vm and the phase will be theta. And we can write this term in terms of phasor as the amplitude Rim, phase theta. As well, we can rewrite the current in phasor domain as Im as the magnitude and phase theta in the angle part. Dividing by voltage by the current will give you the impedance. So as you can see, voltage divided by current in phasor domain will be the magnitude of the voltage Rim, and the phase of the voltage is theta divided by the current, which is Im divided by same angle theta. Ims cancels. The phases divided by each other means they subtract from each other. So theta minus theta is 0. So the impedance will be R as the magnitude and 0 as the angle. As you can see, the real part is the R, but complex part is J0. And if you look at this graph, because the phase is 0, you can simply see that when the current peaks, the voltage peaks at the same location, because the angle difference between the current and the voltage is 0. They peak at the same location, or they get 0 at the same location. Now let's look at another example in terms of the capacitor. We can simply write the characteristic of the capacitance as C times derivative of voltage. That's equal to current of the capacitor. So if we assume the voltage is Vm times cosine omega t plus theta, the derivative of this voltage will be minus omega sine omega t plus theta, and there is a Vm at the beginning, so we put it at the Vm. So this will be your current, but we need to convert this to the cosine. So to change a sine to the cosine. As you can see, we add 90 degrees and we do that at the 90 degrees, but at the beginning, the minus becomes plus, okay? So basically we use a calculus term and to rewrite the current in terms of cosine. And writing this voltage and current in terms of phasor, we take the amplitude, Vm, we take the phase, theta, and writing the current phasor, we take the amplitude of the current, C WVM, C omega Vm, and we take the phase of the cosine and we write that. And dividing voltage by current will give you the impedance of the capacitor. So as you can see, omega C Vm is the amplitude of the current and Vm is the amplitude of the voltage. So dividing each other will give you the amplitude of the impedance. But we have the phases. So this is theta and this is theta plus pi over 2. And when we do the division, it is Vm's get cancelled. So we have 1 over omega c, but the theta minus pi over 2 gives you the angle of minus pi over 2. So minus pi over 2 in terms of angle means exponential j minus pi over 2. So minus pi over 2. So as you can see, in Euler tells us this is exponential minus 90 degrees. So we are here in polar form. And this corresponds to j, minus j, right? So if this is corresponding to minus j, that means instead of this term, we can write minus j here. Or we can rewrite this as 1 over j omega, right? So this is the impedance of the capacitor. If we look at the inductor, well, it is very similar in terms of the terms. So the current on the inductor will be, let's assume Im cos omega t plus theta. So that has a phase Im and that has the angle theta. And we use the characteristic equation of an inductor. Voltage equals inductor times current's derivative. So we take the derivative of the current, rewrite the voltage on the inductor. It got its sign. We convert it to cosine. So that's the voltage of the inductor. And rewriting this, we can get the polar form. So dividing voltage by the current, V over I, gives you the impedance of the inductor. So the amplitude is omega L Im. Current's amplitude is Im. So the amplitude of the phasor will be omega L. Phase of the voltage is theta plus pi over 2. The theta of the current is theta. So the theta, they get cancelled since we subtract each other. So the angle becomes pi over 2, which means j. So we can rewrite this as j omega L as the impedance of the inductor. Also, there is a term called admittance, which is the inverse of an impedance. So 1 over z, which is admittance, will be 1 over j omega L. So as you can see, in the capacitor case, voltage lags current, and in the inductor case, voltage leads current. Well, what does this mean? This means voltage is coming after the current, and in the inductor case, voltage is actually coming before the current. So why is the case? Well, let's look at the time domain signals again, and as you can see, the phase of this time, the current in time is theta plus pi over 2. And the phase of the voltage is only theta. So obviously, as you can see, the theta is less than theta plus pi over 2. That means the current comes before the voltage. Similarly, in the inductor, the current has the phase of theta and voltage has the theta plus pi over 2. Therefore, voltage will come before the current. So voltage leads the current by 90 degrees, or a period divided by 4.